A display controller is a circuit or subsystem in a computer. It is used to output text and graphics on a display monitor screen as an output device. The display is a generic term which refers to all types, from old glass topped bulky boxes to modern LCD, LED monitors and TV. Within a PC, this controller circuit was mounted in a card plugged in motherboard. That card is popularly called as display adapter or display controller. This controller circuit card is called by various other names as video card, video adapter, display card, graphics card or frame buffer. We will first discuss the general details of various cards available, their attributes and their history, and then take up its internal working. Initially, CRT monitors and associated electronics used to be huge standalone box or unit called as computer terminals. Figure 1 shows one such popular computer terminal called DEC VT100. Later on, when personal computers appeared in 1970s, they included a controller circuit to drive TV sets as monitors. Modern display controllers and adapters begin with IBM PC providing a pluggable card or adapter as display controller driving a TV monitor. Table 1 describes various types of adapters or display controller cards with their resolution and color capabilities. The color graphics adapter CGA was introduced in 1981 in IBM PC. It was designed to provide text in 80 character by 25 rows and graphics in 320 by 200 dot resolution in 16 colors. The resolution could be doubled to 640 by 200 dots, but number of colors were reduced to just 4. It could connect to a digital CRT monitor display through a 9-pin connector with digital signals, or it could be connected to a standard TV directly through a single pin RCA connector. Figure 2 shows the computer, the display controller card and the monitor. Note the 9-pin video connector and round RCA connector at the edge of the card. For those users who wanted finer text but no colors, IBM introduced another adapter called monochrome display adapter MDA. Its resolution was improved to 720 by 350 and it could show same text in their finer form. A competitor company, Hercules Computer Technology, in 1983 introduced a display controller card which combined IBM's text only MDA display standard with a bit mapped graphics mode. It became de facto standard on IBM PC compatible clone computers in later years. Figure 3 shows Hercules graphic cards with parts annotated. In 1984, IBM developed Enhanced Graphics Adapter EGA, which superseded and exceeded the capabilities of the CGA. It offered a resolution of 640 by 350 with 16 possible colors. Video Graphics Array VGA refers specifically to the display hardware first introduced with IBM PS2 line of computers in 1987. It used a 15-pin D subminiature VGA connector, which is in use even today in our laptops and desktops. Its resolution was 640 by 480 and 16 colors were supported. First time in display controllers, it employed a video digital to analog converter or DAC chip. that chip could produce hundreds of color shades as per new standard named as amplitude modulated computer display. It was officially followed by IBM's extended graphics array XGA standard, but was effectively superseded by numerous extensions to VGA made by clone manufacturers. These were collectively known as Super VGA or SVGA. SVGA also came in 1987 and its numerous versions progressively supported higher and higher resolutions such as 800 by 600, 1024 by 768 and 1280 by 1024. Today, the SVGA analog interface is used for high definition video including resolutions of 1080p and higher. These are available to users in resolutions up to 2560 by 1600. Currently, the total color shades available are about 16 million. Let us now discuss how the controller works internally. 2.1 CRT display. We should visualize the whole CRT screen as made up of a series of dots which may be white or black. The complete image or picture or text shown on the screen can be visualized as made up of a series of dots, some white and some black. These dots are also called as pixels or picture elements. An image can be made more realistic if white is further divided into a series of gray levels 0% to 100%. Gray levels are achieved by controlling the number of electrons hitting the beam at any instant. More electrons means brighter dot and less electrons means dimmer dot. A display will show a picture very correctly if there are very large number of dots on screen. Higher the number of dots, finer will be its granularity and image will look closer to reality. The term screen resolution is used to indicate the number of dots used to represent the screen. A term like 640 by 200 resolution would indicate that picture is made up of a dot matrix having 640 dots in horizontal row and 200 dots in vertical column. Inside a monitor, the cathode ray tube carries an electron gun which emits electrons impinging on inner surface of glass screen coated with phosphor paint. Figure 4 shows basic CRT structure. Whenever the beam is turned on, electrons hit the phosphor and light is emitted. This is white dot. If beam is turned off, no electrons reach coating and the screen remains off or black. The control signal to operate the beam is called as video signal. A pair of deflection coils moves the electron beam horizontally and vertically using magnetic field. A CRT tube with associated drive circuit is popularly known as CRT monitor or video monitor or simply display. It expects CRT controller to provide driving signals for its deflection coils and video signal to control its electron beam. 2.2 Character generation. CRT monitor is called as raster scan display. In a raster scan, an image is subdivided into a sequence of horizontal strips known as scan lines. Following figure 5 shows the movement of electronic beam. First, the beam moves from left to right in horizontal fashion and displays some information on screen by turning on or off the video signal. That causes bright line or dark areas on the screen. Then the beam retraces back from right to left as shown in dotted line. This is horizontal retrace, and during this period the video is turned off. It takes about 50 to 64 microseconds to complete one scan line, and this is represented by H sync signal. After all the horizontal scan lines are completed, the beam reaches the bottom of the screen and one page is completed. Then it returns back to top left hand position on the screen in vertical retrace. During vertical retrace, the video is kept off. It takes 10 to 20 milliseconds to complete all scan lines needed for 25 rows. Thus, the whole screen or complete image is refreshed 50 to 100 times per second, but it appears to human eye as stationary due to persistence of vision. Each character is drawn in a 7 by 9 matrix as shown in figure 6 below. Each row in above matrix is shown on one raster or scan line. So, it would take 9 scan lines to completely display a character. The character box is of bigger size, that is of 9 by 14 dots. 2 rows and 2 columns on each side of actual character are left blank to provide some gap between adjacent characters and between adjacent rows. One row is reserved for showing underlining if necessary. On screen, the black dot means turn on the beam and white dot means turn off the beam. Each character row takes 14 scan lines or horizontal lines of the matrix. In each scan line, CRT monitor scans the electron beam from left to right, and in that period all the bits in one line of character matrix are displayed. One scan line shows one line dot pattern for all 80 characters. This way 14 scan lines complete one character row. 2.3 Block diagram of display controller. Let us now focus on display controller. Figure 7 shows display controller with reference to CPU and CRT monitor. The CPU writes the data to be displayed into display controller through its system bus. The display controller in turn translates this information and provides it in suitable format to CRT monitor. Following figure 8 shows internal details of display controller. Its main parts are: 1. 6845 CRT controller. This IC was developed by Motorola and it became very popular in many computers in those days. This IC converts text data into bits needed to turn off and turn off the video signal. It also generated horizontal and vertical scanning signals H sync and V sync to drive deflection coils in CRT monitor. 2. Video buffer memory. This is also called as frame buffer. CPU writes the text characters or images in this memory. The 6845 controller reads the data from memory and shows it on CRT. Memory is shared between these two activities. 3. Character generator ROM. The text is usually stored in memory in ASCII code. It is read out from memory and fed to ROM as an address input. ROM output is dot pattern of one row of matrix having a total of 7 columns and 9 rows. 4. Parallel to serial converter. CG-ROM output is 7-bit number which is loaded in a shift register and serially shifted out. The shifting is done at video frequency between 16 megahertz to 100 megahertz. 5. Video control circuit. This circuit uses shift register output bits to turn on and off the video signal on CRT screen. The row bits are further modulated here by a number of attributes such as inverted video, underscore, blank video or blink video. 2.4 Video attributes and generation. All CRT monitors offer many video attributes which allow the text or graphics on display to be more readable and enhance information content. Most of these attributes are implemented by 6845 controller and video control circuit. These attributes are: 1. Reverse video. In standard display, logic 1 in CG-ROM will mean a bright spot on screen and logic 0 would mean darkness or blank. When reverse video attribute is enabled, then over that region the inverted video signal is fed. So, black appears as white and vice versa. 2. Underlining. Usually up to 3 scan lines below any character are kept blank or off. Underlining can be done by enabling video during one scan line below any character. Usually this is also done over an area such as a word or sentence or paragraph. This is done by ORing video with logic 1 during this region. 3. Blinking. Character blinking is achieved by blanking and unblanking character video with a slow frequency signal of 1 to 3 Hz. Whenever blinking is desired over a region, during that portion video signal is ANDed with low frequency signal, and in rest of the region it passes as it is. 4. Blanking. During a character or group of characters, the video is turned off, so screen appears blank there. This is done by ANDing video bits with 0 over that region. 5. Intensity. When this signal is true, the video signal over the region gets higher brightness than normal. So, that portion appears highlighted or prominent and catches attention. This is done by forcing more electrons in beam. The construction of color CRT monitor is different from simple CRT display. It has 3 electron guns or beams, each individually controlled by its video signal. The phosphor dot on glass surface comprises of 3 closely spaced color pixel, red, green and blue. Each electron beam falls on respective dots and generates respective color. When all 3 beams fall on all 3 dots with equal intensity, then white light is produced. When all 3 beams are off, then dark dot is created. If the 3 beams have different values, then dot of different shades of colors is generated. So, in monochrome we have to control only one beam by intensity. Here in color we have to modulate 3 color beams based on color attribute bits stored in video memory. In color display adapter, each character in buffer memory carries a color attribute. Here the text information is stored in 2 parts. One part contains ASCII code for character to be displayed and other part contains bits to specify color shade. The color bits are fed to control individual RGB intensity control inputs of the color display. The number of bits used to represent the color component R, G and B decide how many shades color would be created. This began with a small number like 4 or 16, and now as many as 16 million colors are available in modern monitors. The earlier discussion about use of video memory by 6845 CRT controller is known as frame buffer method. The CPU has to do all the work mainly to store the data in frame buffer. As the images became complicated and bigger, the CPU took very long time to create image or to write image, which became unacceptable. To solve this, the designers took 2 approaches: video accelerator and graphic coprocessors. These are discussed here in some details. 3.1 Video accelerator. An accelerator is a special purpose graphics chip that knows how to perform graphics tasks faster than CPU. First of all, the video memory or frame buffer is kept in main memory, where CPU can write into it at a fast speed. Secondly, accelerator chip reads from main memory into its own local video memory in DMA mode, which is several times faster. Lastly, it performs large amount of copying bitmap memory from one part of video memory to another at a very high speed. The rate at which data is transferred from video memory to screen is also several times faster than what 6845 could do. An accelerator also knows how to build simple geometric shapes such as lines or circles. It performs CPU-like functions in doing simple calculations and draws polygons in video memory. It not only saves CPU times, it also does these tasks several times faster than CPU itself. 3.2 Graphics Coprocessors or GPU. A graphics processing unit GPU is a specialized processor designed to rapidly manipulate and alter memory to accelerate the creation of images in a frame buffer. It can be considered as a computer unto itself. GPUs are popularly used today in embedded systems, mobile phones, personal computers, workstations and game consoles. In a personal computer, a GPU can be situated on a video card, or it can be embedded on the motherboard, or it can be on the CPU chip itself as APU or accelerated processing unit. A graphics chip performs speeding up through the graphics pipeline in two major stages: 1. Creating geometry, and 2. Rendering the final image in dots or pixels. The tasks earlier performed by the main CPU are now done by geometry stage, and it handles all polygon activity and converts the 3D spatial data into pixels. The rendering stage, handled by the 3D hardware accelerator, manages all the memory and pixel activity and prepares it for painting to the monitor. All that remains is shifting out these bits from video memory to monitor. NVIDIA in 1999 marketed its chip GeForce 256 as the world's first GPU. It was presented as a single chip processor with integrated transform, lighting, triangle setup, clipping and rendering engines that are capable of processing a minimum of 10 million polygons per second. It is shown in figure 9. Rival Technologies coined the term Visual Processing Unit or VPU with the release of Radeon 9700 in 2002. To put things in perspective, we have come a long way from first CGA cards having a very low resolution, small 64 kilobytes of frame buffer, fewer colors and tens of milliseconds required to draw a colored circle or a polygon on the screen. The modern options such as GeForce 256 chip, which has 23 million transistors, delivers 15 million polygons per second, 480 million pixels per second and supports up to 120 megabyte of internal frame buffer memory.